guys, I'm Yashvardhan Marda. Today I'm going to be talking about electric field. So let us say we have a point charge plus Q here, and let's say it makes a field like this, and let's say we take another charge plus Q naught here, and this charge is initially at infinity, and then this charge, we take this charge and we put it over here. So this is the initial position, and this is the final position of this charge. So we have taken this charge from infinity and put it over here, and the distance between these 2 point charges is r. So we know from Coulomb's law that the force acting here between the two charges will be k q naught over r square. So this is actually the force. Let's say this right here would be the force. Let's label these points A and B. Force on A due to B. So this is the force on A due to B. This is K Q naught over R squared. So we also know that the force acting on Q naught is F. So force acting on unit charge would be F over Q naught. And this is what we assume as electric field. So electric field is F upon Q naught, and this is in fact electric field is K Q naught over R squared into 1 by Q naught. Q naughts get cancelled, so electric field is equal to KQ by R squared. This is the formula for calculating the electric field. As we can see that from here, electric field does not, basically this is our source charge, the charge which is creating the electric field, and this right here is our test charge, which we have brought in from infinity to a distance r from point B. So we can see that electric field only depends upon the source charge and it does not depend upon the test charge. So this is the formula for calculating the electric field. Now let us talk about the units and dimensions of electric field. We know that electric field is equal to force upon Q naught, put in the vector signs. So, and another formula of electric field is actually, it's minus dV upon dr. V here is the potential difference, R is again the distance. So the SI units are actually here. From this we can see that the unit would become, forces unit is Newton and Q naught is Coulomb, so Newton per Coulomb, and from this we can see that the unit would become, so we can just neglect the minus sign here, so the unit of potential difference is volt and R is meter, so volt per meter. So it can either be Newton per Coulomb or it can be volt per meter. And when we talk about its dimensions, we know that the dimension of force is mLT minus 2 and the dimension of Q naught is 80. So the dimension of electric field becomes M1 L1 T minus 3 A minus 1. This is the dimension of the electric field. Let us understand some of its applications. So from the previous video, we saw that in Coulomb's law there were 2 point charges here, 2 balls let's say, or 2 point charges we can assume. This is of plus Q1 and this is plus Q2. This is falling and the weight would be acting downwards, but from Coulomb's law a repulsive force would act on this ball A. This is force on A due to B. So from Coulomb's law we saw that FAB is nothing but mg, and this is actually KQA QB over R squared is equal to mg. QB is actually Q1 Q2 over R squared is equal to mg. Now let us say we have the same ball here plus Q1 charge, and instead of another ball we have a metal sheet which is positively charged. Now what would happen is that when this ball would fall, the weight would be acting downwards and the force of repulsion would be F, but we would not replace F here by Q1 Q2 by R squared, because that is for point charges. What we will do is that F would be equal to mg, and since we already know that electric field is equal to F upon Q, so from here we get that F is equal to QE. Now equating 1 and 2, we get QE is equal to mg. I'll just rub this. Now let us say that instead of this ball here, we have another metal sheet which is positively charged, and this is another metal sheet which is positively charged. Let us say the distance between these two metal sheets is d. The potential difference of this sheet right here is, let's say, V1, this is V2, and let's say the potential difference is delta V. Let's say delta V is V1 minus V2, and let's say V1 is greater than V2. So this is plus Q1, this is plus Q2, this is falling, so mg would be acting downwards, and again a force would be acting F upwards. Same thing would happen here. F is equal to mg, F is nothing but QE, so QE is equal to mg, and now we know that electric field is equal to potential difference upon R. We can neglect the minus sign here, so from this we can replace that QE is the potential difference delta V, which is V1 minus V2, divided by the distance, which is d, is equal to mg. Let us take an example of a pendulum here. Its bob is positively charged plus Q1, and the electric field, the direction of electric field, let's say, is from left to right like this. So after some time we would see that this bob would become like this, plus Q1, because of the electric field. Electric field is in this direction, tension T is T here upwards, this is theta, so this would become T cos theta, and this is T sin theta. The direction of force is always in the direction of the electric field, so force here is F, weight mg downwards, so T cos theta is equal to mg, T sin theta is equal to F. F is nothing but, we need to now put F in terms of E. We cannot put K Q1 Q2 by R square, because here electric field is given and not a point charge. So T sin theta is equal to, F is actually QE. So this is our first equation and this is our second equation. Now suppose we need to find tension T. So what we can do is we can square and add these two equations. So we would get T square cos square theta plus T square sin square theta is equal to m square g square plus q square and e square. So sin square theta plus cos square theta is equal to 1. Taking t square as common, we get t square is equal to m square g square plus q square e square. So t is equal to under root m square g square plus q square e square. This is the formula for tension. Suppose we were to find tan theta here. So just dividing these two equations, we would get tan theta as QE over NG. Let's say we have a positively charged metal sheet here, and a negatively charged metal sheet here. Let's say an electron is embedded here. So after some time, and this is initially at rest. So initially at rest, after some time the electron would be attracted towards the positively charged sheet. So let's say at this point the electron is like this. The direction of electric field is always from positive to negative. So direction of electric field is like this, and electron is moving upwards. So if we need to calculate the time taken for the electron to reach upwards, we know that initially the electron was at rest. So initially its speed was u is equal to 0 meters per second, right? And the force acting on this electron is F is equal to ma. F is nothing but QE is equal to ma. Q here is the electron itself, so EE is equal to ma, and acceleration of the electron is EE upon m. So we have U, we have A. Let's say the distance between these two metal sheets is D. So the distance the electron is traversing is D. Let's say the time taken is T, which we need to calculate. So from the second equation of kinematics, we know that S is equal to ut plus half at squared. U here is 0, so this gets cancelled out. S is actually D, so D is equal to half times A is EE upon m, and T is T square, which we need to calculate. So T square here is equal to 2mD upon EE, and T is equal to under root 2mD upon EE. This is the time taken to reach upwards. Once again, these two are, this is a positively charged metal sheet, a negatively charged metal sheet. Electron initially at rest, that means initial velocity is 0 meters per second. Acceleration is towards upwards, and we know that force acting on the electron is ma. QE is equal to ma. Q is nothing but E. EE is equal to ma. A is equal to EE by m. S is nothing but the distance. T we need to calculate, so S is equal to ut plus half at squared. U is 0, so this term gets cancelled. S is D, so this is half. A is EE upon m, and this is T squared. M is actually the mass of the electron. Alright, yeah. So time taken is actually under root 2mD upon EE. So this is the time period of the metal sheets. Now if we were to calculate, let's say we need to calculate the trajectory. So for that, let us say this is the positively charged metal sheet. This is the negatively charged metal sheet. This is the electron. It's moving like this, and it would move towards the positively charged metal sheet, and this would actually, so what is happening is that when the electron is in free space, it would move in a straight line. On the other hand, when the electron is the electron is actually here attracted towards the positively charged metal sheet, so it would move like this, and this trajectory is a parabola, and we need to firstly prove that this is a parabola, and then after the influence of these two metal sheets has been totally reduced, it would again move in a straight line. So this is the electron here. Let's say the displacement in x is x, this is y. Here let's say the force acting on electron is F is equal to ma. F is equal to QE, which is equal to ma, and this is the acceleration in y direction, which is EE upon m. X is equal to uxt plus half axt squared. This x, let's say the initial velocity in x direction is v naught. So this is x is equal to v naught t, and acceleration in x direction here is 0, because you can see that the force would act on the electron in this direction. So acceleration would only be produced in the upward direction, that is the y direction. So here acceleration in x direction is 0. X is equal to v naught t. Now y is equal to uyt plus half ayt squared. So y here is equal to, initial velocity in y direction is 0 because it is only moving in the x direction. So uyt is 0. Initial velocity in y direction is 0. This is half. Ay is E by m, and t squared here is, t is x upon v naught. So t squared would be x squared upon v naught squared. So this is the equation for y, and this is the equation for x. Now if we were to find the displacement, this displacement, we can just apply Pythagoras theorem. After applying Pythagoras theorem, we get, let's say this is A, this is C, this is B. So AC, which is the displacement of the electron, is under root x squared plus y squared. So AC is equal to under root x squared here is v naught squared t squared plus y squared here is half E upon m x squared upon v naught squared. This is the displacement. If we were to calculate its final velocity, okay, so we know that y is equal to uyt plus half ayt squared, and y is equal to uy is 0, so this is half ay is E upon m, and t squared was x square upon v naught square. We can see that all these terms right here are just constants. Mass of electron, initial velocity, capital E, small e, 1 by 2, all are constants. So we can say that y is proportional to x squared, and this in fact proves that this here is a parabola. This is a parabola, and after the point C, it moves in a straight line. Let's say we were to calculate its final velocity now. So we know that final velocity is equal to ux plus axt. We know that ax is equal to 0 and uy is equal to 0. So vx is nothing but, ax is 0, so vx is nothing but ux, and that is vx is equal to v naught, because ux is v naught here. Vy is equal to uy plus ayt. Uy is 0, so Vy is equal to, Ay is E by m, and time is, let's say, we can take t also, or let's say x by v naught only, since we know that x is equal to v naught t. So t is equal to x upon v naught. So Vy is this. So the magnitude of the velocity would be under root Vx square plus Vy square. So the magnitude of the velocity is equal to under root Vx square is v naught squared plus Vy squared is this. This is e square by m square x squared by v naught squared. This is the velocity, final velocity after the point C. Let's say we have a triangle here. These two sides are equal. This is a right angled isosceles triangle. Let's say these two sides are AA. This is A, this is B, this is C, this is point P. Here plus Q1 charge is there, here plus Q2 charge is there, and here a plus Q3 charge is there. Now we need to calculate the net electric field on point P. So electric field on point P due to point A would be away from the charge here. Electric field on P due to A. Electric field on P due to C, again since this is plus, so away from the charge. And electric field on P due to B would be away from the charge in the line only, along the line. So this is on P due to B. So we can see that these two electric fields are equal in magnitude as well, and let's say these are in fact plus Q charges. So these two electric fields are equal in magnitude as well as opposite in direction. So they get cancelled out. So the total net electric field on point B would be just due to electric field on point B due to B. So electric field on point P due to B is the net electric field on point P, which is equal to K. Okay, since these two sides are equal, this is 45, this is 45, this is 90, so this is 45. Yeah, so we can take sine 45 is equal to perpendicular, which is BP upon hypotenuse A. So BP is equal to A sine 45, and sine 45 is 1 by root 2. So BP is equal to A by root 2. So this is K. Now Q is QB. QB upon BP squared. This is the net electric field. And the direction is BP cap. This means towards BP. Towards BP we can say, or along the line BP we can say. So this is K, QB is plus Q, which is upon BP whole squared is A by root 2 whole squared. BP cap is the direction. This is a unit vector and it indicates the direction. So this is KQ upon A squared upon 2 would get up. So this would be 2KQ A squared BP cap, and this can be written as K is 1 by 4 pi epsilon naught into 2Q by A squared BP cap. This is the net electric field on point P. That is all from electric field from my side. I hope you all enjoyed the video. Please like, share, comment and subscribe to my channel if you haven't done yet. And I'll see you all in the next one. Thank you.